continue the recording. So in this case, we're looking at measuring the volume in a burette. So we've established previously in this problem, working through this problem, that 1 tick is equal to 0.1 milliliters. So we can report up to 0.01 milliliters. So reading through in this case, so we make our measurements from the bottom of the meniscus. In this case, we can report our certain digits, which would be 15.2, and then we can estimate an additional digit. So this would be about 15.25 milliliters for our initial volume. Does that first part make sense? Does that first part make sense to everyone? So for our final volume, we can report our certain digits, which are 17.3, and then we can estimate an additional digit. So now that we have our initial and final volume, we can calculate the volume of liquid dispensed by taking V final minus V initial. So the volume of liquid in this case would be 17.30 milliliters minus 15.25 milliliters, which gives us 2.05 milliliters. Does this make sense to everyone? Does this make sense? Any questions on this for this first problem? So I'm just going to save that in the chat because we'll use that later. May I clear this first discussion? Is everyone comfortable with this first portion? Don't be shy to type in the chat or let me know verbally if everyone's comfortable with this. Does anyone have any questions on this logic? Any questions? So looking at the next part of this problem, so we recorded the initial, final, and we figured out the volume of liquid. We're next given some mass data to work with. So we have our empty beaker, and the mass of this beaker was found to be 13.503 grams. If we placed our liquid sample in the beaker, the mass was found to be 15.162 grams. So then we can figure out the mass of the liquid via difference. So we take 15.162 grams minus 13.503 grams, and that in turn gives us a mass of liquid of 1.659 grams. Does that make sense to everyone? Any questions on this idea of weighing by difference?
Professor, sorry, what question it is? I just joined in. I'm kind
of... yeah, we're continuing on with question 33 through 37. So this mass calculation is for question 37.
37, okay, thank you.
And in the chat, I recorded the volume and mass that we calculated from these procedures.
Okay.
Does that make sense?
Yes, thank you.
Perfect, perfect. Any other questions? Now that we have the mass and the volume, we have enough pieces of information to calculate the density. So we know that the density is equal to the mass over the volume. So we take our mass of 1.659 grams over the volume of 2.05 milliliters, and that gives us our density of 0.809 gram per mil. This is very similar to the question that you had in the lab, except this time you're looking at a liquid and you're measuring the volume using a burette. Does that make sense to everyone? Any questions on this example? Okay, if not, let's keep going now. Now that we've calculated our density to be 0.809 gram per mil, we're asked to calculate the mass of 2 liters of this liquid. Okay, so let's go to the whiteboard now. So let's look at the information that we have. So we know that our density is equal to 0.809 gram per mil. We know our volume is equal to 2 liters. So we know that mass is equal to density times volume. So we have 0.809 gram per mil. We have 2 liters, and we know that in order for these units to cancel, we need to convert liters to mils. So we know in 1 milliliter, we have 10 to the negative third liter. Oh, is everyone able to see the recording? Is everyone able to see this recording?
Yes.
Yes.
Are there any technical issues? I just got an email that a student was having trouble viewing the recording. Is it okay now? Is the stream visible and is everyone able to see my screen?
You got the email from me?
Yes.
No, that was the time we were waiting for you.
Ah, okay, perfect. Sorry, I'm just making sure.
No, it was from before this, sorry.
Oh, no problem at all. Okay, perfect. So then we'll continue on then. So we have our mass calculation by taking density times volume. Okay. Now the tricky part is we need to convert our volume from liter to milliliter. So we need to perform this conversion in our mass calculation. Punching this into our calculator, that in turn gives us 1,618 milliliters that we round to 1 sig fig, which would be 2,000 milliliters. Does that make sense to everyone?
Professor, in Canvas, I put 2,000 and then it shows correct answer as 1,580.
Yes. So sometimes if there's drift between the numbers, if your density is a little bit different, there's going to be a pretty wide range. So I'll go through and check your answers by hand. Yeah, I use, when I did my key preparation, I may have measured the masses and volumes with a slightly, not in a slightly different way, but the measurements will have a little bit of variation, and that can result in pretty large changes in your calculated density.
Mm-hmm.
Does that make sense?
Yes. So I get credit, right, for that
Yes.
2000.
Yeah.
Okay,
Mhm.
great.
So looking at the next part. So given the following table, we're asked to identify the unknown liquid. Given that our density is equal to 0.809 gram per mil, which sample has the closest density? Which sample is the closest match to 0.8?
I pick acetone, but
Yep,
again,
yep.
is wrong.
No, that's correct. It was only marked because it was misspelled.
Okay.
Yep. Mhm. Does that make sense? So we matched it with acetone because these densities are the closest in terms of percent difference. Okay, so let's keep going with this. As you see, we're making pretty good progress through this exam. Now we're asked the question in 42, what volume of pyridine would have the same mass as 12 liters of the unknown liquid? Keeping in mind that pyridine has a density of 0.98 gram per mil. So we got that from the table. Okay, so we know, so in this case, we're going from the volume of our unknown to the mass of our unknown to the volume of pyridine. Okay, so we have 12.00 milliliters of our unknown. We know that to go from volume to mass, we use our density. We have 0.809 grams per mil. And to go from mass to volume, we're going to divide by our density. In 1 milliliter of pyridine, we have 0.98 grams. So punching this into our calculator, that in turn gives us 9.906 milliliters, which in turn gives us, rounding to to 2 sig figs, 9.9 milliliters. Does that make sense to everyone? Does this idea make sense?
Professor, I don't understand this question at all.
Okay, so just to talk a little bit about this, we're asked what volume of pyridine would have the same mass as 12 milliliters of unknown liquid. So in the first step, we can calculate the mass of our liquid by taking the density times the volume. And that in turn, we take 12.00 milliliters times 0.809 gram per mil. That gives us a mass of liquid. That gives us a mass of liquid of 9.708 grams. Now, from this information, what we can do then is we can figure out the volume of pyridine by taking the mass of pyridine over the density. And the mass of the liquid is equal to the mass of pyridine in this problem. So we plug in the mass of our liquid and we divide by the density of pyridine, and that gives us the volume of pyridine that has the same mass as our unknown liquid. Does that make sense?
Yes, thank you.
Perfect. Any other questions on this example? Okay, so let's look at the next set of questions in this exam. So this question was a little bit tricky, but nothing that we can't handle. So we're asked to carry out the following unit conversion. Okay, so in this case, we want the volume in cubic centimeters. So we need centimeters. I'm just going to put that up here. Given the dimensions of inches by feet. So I know that I have 2.54 centimeters per inch, and I have 12 inches in a foot. So for 5.00 inches, to go from inches to centimeters, I need centimeters on top. So I have 2.54 centimeters per inch. Okay. That in turn gives us 12.7 centimeters. When we have 1.50 inches, we know that we have 2.54 centimeters per inch. And that in turn gives us 3.81 centimeters. For 0.50 feet, we know that there are 12 inches in a foot and that there are 2.54 centimeters per inch. That in turn gives us 15.24 centimeters. So now that we have each of these lengths converted, we can calculate our volume by multiplying our length, width, and height. Keeping in mind that this is a multiplication operation where our least precise input has 2 sig figs. So punching this into our calculator, that in turn gives us 737 centimeter cubed that we round to 2 sig figs, or 740 centimeters cubed. Does this make sense to everyone? Perfect. So let's keep, oops, one moment. So let's keep going with this. So we're asked to carry out the following operation. In this case, we're asked to calculate percent error. So in this case, we know that percent error is equal to our experimental value minus the literature value over the literature value. So let's compute these calculations step by step. So this first operation, this first subtraction operation, for subtraction, we're concerned about the least number of decimal places. So we'll retain 3 decimal places. Now that we've completed the subtraction operation, we're now dealing with a multiplication and division operation, which cares about significant figures. And as we can see, the top number only has 3 significant figures. So when we take 0.201 divided by 24.305 times 100, we get out for our percent error 0.8269 that we round only to 3 sig figs, which gives us 0.827%. Does this idea make sense to everyone? This is an example of sequential operations and significant figure rules dealing with sequential operations. Does this make sense to everyone?
Yes.
Perfect, perfect. So let's keep going with this. And let's look at the next question. In this case, we're asked to perform a unit conversion. So we're asked to convert each of the following to the indicated units. So we're starting off with units of micrograms per microliter. We're always going to go through our base units. So we know we're going to go from micrograms to grams, and then to nanograms, and then from microliter to liter to milliliter. So with this solution map established, we have 1.450 microgram per microliter. We know that there are 10 to the negative 6 gram per microgram. And we know in 1 nanogram, we have 10 to the negative 9th gram. So we've checked off this first conversion. Now we're going from 1 over microliter to 1 over liter. And we know in 1 microliter, there are 10 to the negative 6 liter. And we know that there are 10 to the negative 3rd liter per mil. So punching this into our calculator, we get 1.450 times 10 to the 6th nanograms per milliliter. Does this example make sense?
Yes.
Perfect, perfect. Any other questions on this example? Okay, so let's keep going then. In this case, we're asked to write the abbreviated electron configurations. So for boron, our abbreviated electron configuration, the preceding noble gas to boron is helium. Then we fill our 2s orbital followed by our 2p orbital. These electrons are core, while our electrons with the largest N value are the valence electrons. Does this make sense to everyone? Any questions on this example?
So Professor, the 2s2 and 2p1 are valence, right?
Yes, exactly right. Okay, so let's keep going with this.
Professor, just to add on to that, what would be the inner shell for that? The 1s2, 2s2, and 2p1?
The inner shell would be the inner shell electrons, or core electrons, would be the electrons represented by this abbreviated helium, or these 1s2 electrons. These are our inner shell electrons, because they're closer to the nucleus and they're electrons that are not those with the largest N value. Does that make sense?
Yeah.
Perfect. So let's keep going with this. And let's look at the next example. In 46, we're looking at phosphorus. The preceding noble gas, the noble gas before phosphorus, is neon. Next, we fill our 3s2 and 3p orbitals. These outer electrons are our valence electrons, while these electrons represented by this neon abbreviated configuration are our core electrons. Does that make sense? Perfect. So let's look at another example. This time we're looking at something like strontium. So in the case of strontium, the preceding noble gas is krypton, or Kr. Our outermost electrons are in the 5s orbital, and we have 2. So these outermost electrons are the valence electrons, while those represented by our noble gas core are considered our core electrons, or inner shell electrons. Does this make sense to everyone? Okay, so let's keep going with this. So we're asked to draw an orbital box diagram for arsenic. Okay, so looking at arsenic. So arsenic has 33 electrons to its name. So starting off, I'm going to label my orbitals and draw out my orbital boxes. Okay, now I'm going to fill in my orbitals with electrons from highest to lowest energy. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 31, 32, 33. And remember, you place electrons in empty orbitals before pairing. Remember Hund's rule, otherwise, or the Aufbau principle, both are fine. Both can explain this phenomena. Does this make sense? Does this make sense?
Professor, I have a question about what's the easiest way to download it? Because I just figured out to draw on the paper, take a picture, and then download that to you. Is that the
That's
best
more
way
than
to do
okay.
it?
Yeah, that's more than okay.
Okay.
Any other questions? Yeah, as long as it's visible, even if it's a picture on a piece of paper, that's more than okay. Okay, so let's look at another example. So in question 49, we're asked to draw a series of Lewis structures. So what I'm going to do is I'm going to pull this up into OneNote. Give me 1 second to do that. Okay, can everyone see my screen in OneNote?
Yeah.
Okay, perfect. So let's focus on drawing out the Lewis structures for each of these compounds. So for CH2OH, carbon, we have 4 electrons, hydrogen contributes 2, oxygen contributes 6. So we have 14 electrons to work with. We're going to put carbon as the central atom and surround it with each of our other atoms. Then we're going to form 1 bond each. We have 8 electrons remaining. Sorry, this should be 12 and 6. And our 6 electrons are placed on oxygen. To fulfill the octet rule, we move a lone pair down and form a double bond. And from here, from this structure, this is our complete Lewis structure. Looking at the geometry for carbon, as it has 3 bonded atoms, it would be trigonal planar. And what would the approximate bond angle be for a trigonal planar molecule?
120 degrees.
Yep, exactly right, 120 degrees. Okay, so we'd label this with a bond angle of 120 degrees. Now, looking at this molecule in terms of polarity, does this molecule have polar bonds? Does this molecule have polar bonds?
It does.
Yep, and most importantly, are all of the polar bonds attached to the central atom the same or different?
They're different.
They're different. So as a result, this molecule would have a net dipole and it would be polar. Does that make sense? Perfect. So let's look at another example. In this case, we're dealing with NCl4+. So nitrogen contributes 5 electrons. Chlorine contributes 7 electrons. And don't be shy to unmute to ask a question. So chlorine has 7 electrons and we have 4 chlorines. This gives us a total of 33. And because we have a +1 charge, we subtract 1, giving us 32. So we're going to put nitrogen in the center and surround it with each of our 4 chlorines. And we're going to form 1 bond each. So from our total, we in turn subtract 2 electrons per bond, and that gives us 24 electrons. We then place lone pairs on each of our chlorines, and this is our complete Lewis structure. One thing we have to consider is formal charges, and we see the formal charge of nitrogen, which is the group number minus the bonded atoms, minus the lone pair electrons, and that gives us a formal charge of +1. So we put a plus sign next to nitrogen. So looking at our central atom, what geometry would our central atom have?
Is it tetrahedral?
Yep, exactly right. We have 4 bonded atoms, so this would have a tetrahedral geometry. And what's the approximate bond angle for a tetrahedral geometry?
It's 109.
Yep, exactly. It would be 109, roughly 109.5. Now, in terms of polarity, this molecule does have polar bonds, but is the polarity, are all of our polar bonds arranged symmetrically? Are all of the bonds to our central atom the same?
They're all the same. They're chlorine.
Yep. And because the central atom, it has a symmetrical geometry, all of our bond dipoles cancel out. So all of our atoms bonded to the central atom are the same. All of our bond dipoles are the same. And because our bond dipoles are arranged symmetrically, they end up canceling out.
Professor,
Does
I
that
don't
make sense?
understand why sometimes you calculate the formal charge for some molecules. Like,
The
right?
reason, so in all of these examples, I am sort of in the background calculating it. I wanted to point it out for nitrogen in this case, because the molecule is charged, by definition, there must be a formal charge on one of your atoms.
I
Does
see.
that make sense?
So when the molecule has like plus or minus sign,
Yes.
we find the formal charge for the central atom.
And or all of the atoms. But we found that the formal charge for a central atom is +1.
Okay.
But on your own, you'd like to do a detailed analysis and look at each atom to make sure that that there aren't any other formal charges.
Okay.
Does that make sense?
It does. Thank you.
Perfect. Okay, so let's keep working through these examples. And in this case, let's look at acetic acid, which is CH3CO2H. So first and foremost, in terms of our count, we have 2 carbons. So we have 4 times 2. We have 4 hydrogens, 1 times 4, and 2 oxygens, which would be 6 times 2. So adding up our total, that gives us 24 electrons. We're going to put our 2 carbons as the central atoms, and we're going to surround our carbons with our remaining atoms. Then we'll form 1 bond each. 2, 4, 6, 8, 10, 12, 14. So we've used up 14. We have 10 electrons remaining. We're then going to place our remaining 10 electrons as lone pairs on our most electronegative atom. Finally, to complete the octet on carbon, we're going to convert one of our lone pairs into a double bond. And this gives us the complete structure for acetic acid. So let's look at each of our atoms. And let's assign the geometry. So I'm going to label these 1 and 2. So for carbon 1, what is the geometry? What is the geometry? What is the geometry on carbon 1?
Is it tetrahedral?
Yep, exactly right. Okay, and carbon 2 with its 3 bonded atoms, what's the geometry on carbon 2?
Trigonal?
Yep, trigonal planar. Finally, on our oxygen atom, what would the geometry be when we have 2 bonded atoms and 2 lone pairs?
2 bonded atoms, 2 lone. Is bent?
Yep, exactly right. Perfect. So then our bond angle for tetrahedral will be 109.5. For trigonal planar, it's 120. What about for bent? What's the bond angle for the bent geometry?
Because it has lone pairs, so it's 105.5.
Yes, exactly right. It would be 105.5 degrees. So is this molecule polar? Is this molecule symmetrical? Does this molecule have the same atom bonded to our central atoms? What does everyone think? So we have polar bonds, right? These carbon-oxygen bonds are polar, but are these polar bonds arranged symmetrically? Looking at these arrows, do we see arrows arranged, the bond dipoles arranged symmetrically, or are they pointing in a given direction? Are they what does everyone think? Do these bond dipoles cancel out?
No.
They don't cancel out. Exactly right. So this molecule would be polar. Does that make sense?
Professor, can you go over where you got the 4 times 2, 1 times 4, and then 6
Yes.
times 2?
So for our electron counts, we have 2 carbons, right? So carbon contributes 4 electrons and we have 2 of them. Hydrogen contributes 1 electron and we have 4. And oxygen contributes 6 electrons and we have 2.
I thought we had 3 carbons.
CH3CO2A.
So it has the C and then the C2.
Where's
So
where's
wouldn't
the where's the C2?
so the CH3, so
Yeah.
that carbon would be considered 1 carbon, correct?
Yep.
And then the the CO2.
Yeah. The 2 is only applying to oxygen. If it was applying to carbon, the CO would be in parentheses.
Oh, Professor, mine CH3C2H. I don't have the O.
Oh, yes, that's the next example.
Oh, okay. Oh,
Yep,
okay.
yep.
I was totally confused.
Does that make sense?
Oh, yeah. Oh, oops. I guess I
No,
just
no
completely
problem.
missed one.
No,
I
no, no.
thought they were the same. Oops.
Uh, does that make
Okay.
sense?
Yeah,
Perfect.
thank you.
Mm-hmm. On that note, let's look at this example. As this one, I wouldn't call it a trick question, but it has a little bit of nuance to it. So looking at this case for our electron count, we have 3 carbons. So we have 4 electrons times 3, and we have 4 hydrogens. So we have 1 times 4. That gives us 16 electrons to work with. We're going to put 1 carbon as our central atom and the other 2 carbons arranged as our other central atoms. We're then going to form 1 bond each, 2, 4, 6, 8, 10, 12. So we have 4 electrons remaining, and then we're going to place our lone pairs on our outermost carbon. To fulfill the octet on our middle carbon, we're going to convert our lone pairs, both of them, into a triple bond. So we fulfilled the octet of all of our atoms, and this is our final structure. So I'm going to label my atoms 1, 2, 3. So looking at the geometry, for carbon number 1, what would the geometry be?
It's tetrahedral.
Tetrahedral, exactly right. What about carbon number 2?
So it has
It has 2 bonded atoms, so what would that be?
It is linear.
Yep, exactly right. And carbon 3 would also be linear. So for our bond angles for tetrahedral, we know it's about 109.5 degrees. What about for linear? What's the bond angle for linear?
180.
180, exactly right. Now, here's an important question. Is this molecule polar? So let's think, are carbon-hydrogen bonds polar? Are carbon-hydrogen bonds polar? Are they considered polar bonds? Remember how we talked about in class, hydrocarbons, think like oils, are they considered polar? What does everyone think? So a carbon-hydrogen bond is it's not polar. And since this molecule doesn't have substantially polar bonds, it would be a non-polar molecule. Does that make sense? Any questions on this example? Okay, so let's keep going with this. And now for a somewhat relatively straightforward example, we're looking at PO3 minus. So phosphorus contributes 5 electrons, oxygen contributes 6 electrons, and we have 3 oxygens. We get 23. Since we have a -1 charge, we add 1 to our total to give us 24. Okay, we put phosphorus as the central atom and surround it with our 3 oxygens and form 1 bond each. We're now at 18 electrons. We place lone pairs on each of our oxygen atoms until the octet is fulfilled. We've used up all 18 electrons. And now what we're going to do is we're going to convert one of our lone pairs into a bond. Now from this structure, we're not quite done because we need to assign formal charges. This is a charged molecule. So the formal charge of phosphorus would be 5 minus 4, which is +1. And the formal charge of oxygen, these two bottom oxygens, would be 6 minus 6 lone pair electrons minus 1 bonded atom, which gives us -1. The formal charge of this top oxygen is 6 minus 4 minus 2, which would be 0. Does this make sense to everyone? Does everyone see why we calculate the formal charges in this case and why we're careful with our formal charges in this case?
Professor, for that one, it says 6 minus 6 minus 1. So
Yep.
6 is the group number.
Yep,
And
the
the
group
other 6
number
is the
minus the lone pair electrons and then the bonded atoms.
So it shouldn't be +1?
But we subtract the bonded atoms. So the 6 minus 1 isn't in parentheses. It's like, you can also write it like this. Sure.
Oh, got it. Okay.
Yeah,
I see
yeah.
what you did. Okay.
Does that make sense?
It does. Yes.
Perfect. So looking at our geometry, if we have 3 bonded atoms, what would the geometry be around this phosphorus? What would the geometry be?
So it has 3 bonded, and it's trigonal planar.
Yep, exactly right. And as a result, this bond angle would be 120 degrees. Does that make sense? Perfect. So this Lewis structure section is really important as it comprises a lot of the content that we'll be seeing again when we move on and we start to discuss the organic chemistry portion of this course. So let's keep going now.
So Professor, I have a question about the grading. So like each of them has like 4 or 5 points. Like
Yes.
let's say I missed 2. So you just deduct 10 points, right? It's
Yes.
like, okay.
Each Lewis structure is broken up into individual points for each of these categories, with more points being allocated to the correct structure.
Okay.
So looking at question 50, we're asked to draw an orbital box diagram for calcium plus. So looking at calcium plus, so calcium on its own has 20 electrons. So we take 20 electrons minus the charge, which is +1, which gives us 19 electrons. We then write out our orbital box diagram. And then we fill in our orbital box diagram from lowest to highest energy. 2, 4, 6, 8, 10, 12, 14, 16, 18, 19. Does that make sense to everyone? I chose potassium plus because it's harder to look up and it requires a little bit more of an understanding of counting electrons. Any other questions on this example? Okay, let's keep going then. So now we're asked to draw an orbital box diagram for Br minus or bromide. So let's work on that. So looking in the periodic table, we know that bromine has an atomic number of 35. So our number of electrons is equal to our atomic number minus the charge, which gives us 36 electrons. We then write out our orbital box diagram. And then we fill in our electrons from the lowest to the highest energy orbital. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. Does this make sense? Okay, so let's keep going with this. So in this case, we're asked to write the abbreviated electron configurations. So for sulfur 2-, so our preceding noble gas to sulfur is neon. And so we'd write this configuration with 2 extra electrons. So it would be 3s2, 3p6. With these outer electrons being the valence electrons and the noble gas core being the core electrons. Does that make sense to everyone? Okay, so let's keep going with this. So in the next case, we're asked to write the abbreviated electron configuration for strontium 2+, keeping in mind that strontium typically has 38 electrons. So then strontium 2+ would have 38 minus 2 or 36 electrons. In that case, the preceding noble gas will be argon, and we'd fill in 4s2, 3d10, and 4p6. Only the 4s and 4p electrons would be considered valence, while the 3d and the argon abbreviated electrons would be considered the core electrons. Does that make sense? Oh. Does that make sense to everyone?
Professor, so why we don't put krypton? That's the last one.
The reason for that is that if you write it as krypton, this would also be accepted, but it's more correct if you just have a full noble gas shell to write the electron configuration using the preceding noble gas.
Oh, one before krypton.
Yes, yes.
So if I put krypton and then I put, so then it has any valence electron or it doesn't?
It does. The 4s and 4p would be considered valence.
Okay.
And that's why I wrote it out like this.
Okay, got it.
Perfect. So continuing on. So in this case, we're asked how many significant figures. The leading zeros are not significant, so this number would only have 2 sig figs. In this next number, zeros after a non-zero digit and after a decimal point are significant. So this number would have 6 significant figures. Does that make sense? Any questions on these examples? Okay, let's keep going then. So we're asked how many significant figures are in the following number. 1.9, I see 2 non-zero digits, so this would have 2 sig figs. 1400, these trailing zeros are not significant. These zeros are after a non-zero number, but not in between non-zero numbers or between a number and a decimal point. So this number only has 2 significant figures.
Professor, going back to question 56, so I thought when it was in scientific notation like that, we would assume that the decimal point is there. Is that scientific notation?
Yes, it is. It is. And it has 2 sig figs. Yep, because the 1 and 9 are considered significant.
So then the zeros after that, after we take it out of?
The times 10 to the 8th, this is your exponent. And it doesn't affect the number of sig figs in your number.
I thought that was a scientific notation. Okay.
No, it is. It is. It is. It's 1.9 times 10 to the 8th. But this times 10 to the 8th doesn't affect the number of sig figs in your measurement. It just tells you how large or small your number is.
Okay.
Does that make sense?
Yeah, yeah. So we don't assume that there's a decimal point in there if we write out the number.
There is. There's the 1.9. But like the times 10 to the 8th is not part of the number of sig figs.
Okay, so we don't worry about that then.
Yeah, you just literally like put your hand over it and just look at the base number.
Okay.
Does that make sense?
Yeah.
Perfect. So let's keep working through these examples. So in this case, we're looking at 150 dot. In this case, our decimal makes this trailing zero significant. So we have 3 significant figures. Does that make sense? Okay, so let's look at this next case. We're asked to carry out the following calculation. So thinking about multiplication and division, we care about the least number of sig figs, which is 2 sig figs. So our final answer will have 2 sig figs. And if we punch this into our calculator, we get 1.36 times 10 to the negative 16th that we round to 1.4 times 10 to the negative 16th. Does that make sense to everyone?
Yes.
Perfect. So let's keep going with this. So we answered 50, 59, and 60. So looking at 61, again, we're dealing with multiplication and division, and the least number of sig figs is 3 sig figs. So punching this into our calculator, we get as a total 1.299 times 10 to the negative 6 that we round to 1.30 times 10 to the negative 6. Does this make sense? Does this question make sense? Any questions on this?
Professor, question 60, sorry, I got behind a little. Can I just see the answer, the final answer?
Sure. Just one moment. For question 60, let me.
Oh, you deleted it? That's okay, no worry. I'll look at the recording.
Okay.
Right.
I can calculate it really quickly. It's not a big deal. One moment.
Okay, sorry, thank you.
No problem at all. So that in turn gives us 1.4 times 10 to the negative 16th.
All right, thank you.
So let's keep going with this example. We're almost done. So for the last few sets of problems, we're looking first at an addition operation. And this addition operation, we care about decimal places. So if we have 5.40, so if we have 5.40 plus 12.1 plus 0.55, our least number of decimal places is 1 decimal place. So that in turn, we get 18.05. We round to 1 decimal place. That gives us 18.1. Does that make sense? So continuing on, looking at this next example, we're dealing with a subtraction operation. So we have 12.501 minus 7.10. So we'll retain 2 decimal places, and that gives us 5.401 that we in turn round to 5.40. Does this make sense to everyone? Okay, so let's keep going now. So in this case, we're asked to do a multi-step conversion. In the first case, we're doing subtraction. So 1.50 minus 0.6. So we only retain 1 decimal place. That gives us 0.9. Now we deal with the multiplication operation, which cares about sig figs. 0.9 has 1 sig fig, 3.00 has 3, and that gives us 2.7, which we round to 1 sig fig, which would just be 3. Does
Professor,
this make
Canvas
sense?
also showed this one as wrong. It shows 2.7 as correct answer.
Oh, I can double check, and of course I'm going to go through and regrade this by hand. So there may be some glitches with how Canvas scores certain responses, but I'll make sure to get those corrected.
Okay, good.
So in the next case, we're dealing with another sequential operation. This time we're doing multiplication first. So we have 1.90 times 3.0. And that in turn gives us 5.7. So then we add 5.7 with 2.657, and we retain 1 decimal place. And that in turn gives us 8.357 that we round to 8.4. Does this make sense to everyone? Any questions? Okay, so continuing on, we're going to look at question 67. So we're classifying this compound as ionic or covalent. I see the presence of a metal. And what does the presence of a metal tell us? A metal tells us, do we have an ionic or covalent compound?
An
Ionic.
ionic.
Yep, exactly right. So then, perfect. Now looking at NO2, I see two, whoops, sorry about that. I see 2 non-metals. So would that be considered ionic or covalent? If we have 2 non-metals?
Covalent.
Yep, exactly right. Does this make sense to everyone? Perfect. So let's keep going now, and we're asked to do some simple unit conversions. We're asked how many milliliters are in 154 microliters. So we're going from microliter to liter to milliliter. So in 154.0 microliters, we know that we have 10 to the negative 6 liter per microliter. And then we know in 1 milliliter, we have 10 to the negative 3rd liter. That in turn gives us 0.1540 milliliters. Does this question make sense? Okay, continuing on. Let's look at these last 2 examples. So we're trying to calculate the kilograms given the amount in centigrams. So we're trying to go from centigrams to grams to kilograms. So if we have 357.0 centigrams, we know that we have 10 to the negative 2nd gram per centigram. And we also know in 1 kilogram, we have 10 to the 3rd gram. That in turn gives us 0.00357 kilograms. Does this make sense to everyone? Any questions on this question? Any questions on this problem? Okay, so let's keep going with this. And for our final problem, we're asked to figure out the nanometers present in a given number of millimeters. So we're trying to go from millimeters to meters to nanometers. So starting off, I'm going to write this in scientific notation. So we have 7.5 times 10 to the negative 6th millimeters. We know that there are 10 to the negative 3rd meter per millimeter. And we know that in 1 nanometer, we have 10 to the negative 9th meter. And that in turn gives us 7.5 nanometers. Does this make sense to everyone? So with that, we've concluded the exam 1 review. If there are any other